So today we're very happy to have Meir here, who will tell us about a KRW-like theorem for strong composition in what seems likely to be maybe the last Meow seminar before summer vacation. So please, take it away.
Thank you. Yes, this is the title of the talk, and the talk will go about like this. I'll start with a background in which I'll explain all these terms in the title, and then I'll describe our result and describe a bit about our give a brief overview of our proof strategy, and then time allowing, I'll try to cover two nice ideas from the proof. The proof itself is fairly long, so I won't get to cover it in detail in the first half, but there are still two nice ideas that I would like to describe, and I'll try to do it in the first half. But let's start from the beginning. So we talk about complexity. So of course it is important to set up a computational model. So our computational model will be Boolean circuits with AND, OR, and NOT gates, and such circuits compute a Boolean function over n variables in the natural way. We start by writing the input bit on the input gates and then push them upward on the circuit, and each vertex gate computes the function associated with it and puts the output value further upward until we get the output on the topmost gate. In this talk, I'll only consider circuits in which every gate has at most two incoming wires. We can also consider other types of circuits, but for the purpose of this talk, we will focus on this kind of circuits. Now, one important parameter of circuits is their size, the number of gates in the circuit, which roughly corresponds to the running time of the algorithm on a Turing machine. And we will also be interested a lot in the depth of the circuit, which is the length of the longest path from an input gate to the output gate. Or if you like, you can think about it intuitively as the number of layers in the graph. And even more intuitively, this roughly corresponds to the running time of an algorithm on a parallel machine. Because if we have a parallel machine with an unlimited number of processors, such a machine can simulate every layer of the circuit in one step, but it does need to simulate the different layers one after the other. The depth is the running time on such a machine. Now, now that we have this computational model, well, what we usually want to do in complexity theory is to prove things are hard. That is, that it is hard to compute functions. For example, to say that there is a function f that does not have circuits of polynomial size. Now, there is an easy counting argument that says that, well, there exist some functions that require circuits of almost maximal size, size almost 2 to the n. But this is not a very interesting statement, because those are like very arcane, complicated functions and we don't know really how they look like. We only know they exist. What we really want to do is to prove that there is an explicit function, a nice function that we can describe, for which we can prove such a statement. For example, we would like to prove that there exists such a function f in NP. And that would be great, because if we could prove it, it would prove in particular that P is different than NP. Of course, having said that, this means that this goal is extremely difficult to obtain, and we have no idea how to prove any strong hardness results for general circuits. The best we know is something like 5 times n or something like that. Is the lower bound. That is, we can only prove that there exists a function f in NP that requires circuits of size 5 times n. So what we do in the meanwhile is to try to prove hardness for weaker circuits. That is, instead of considering general circuits, we consider circuits that after we tie their hands behind their back and put something over their eyes, and we try to prove that such circuits cannot compute some function in NP. And the idea is that, well, if we can prove that these kind of circuits cannot compute a function in NP, then maybe we can gradually consider stronger models of circuits. Maybe we can release one of their hands, or maybe we can remove the eye cover and still prove that they cannot compute some function in NP, and then gradually, in small steps, prove that P is different than NP using this strategy. So in other words, we do what every mathematician does when they encounter a very hard problem. They consider toy problems of increasing level of difficulty and try to solve them in this order. In this particular talk, we will consider a weaker model of circuits, which is circuits of small depth. So we will restrict the depth of the circuit. A bit more formally, if we have an arbitrarily Boolean function f from 0,1 to the n to 0,1, we can define its depth complexity to be the depth of the shallowest circuit that computes f, regardless of its size. Now, it is not hard to see that for every interesting function, the depth complexity is at least log n. This is because we assumed that the fed-in of the circuits, that it is the maximum number of wires going into each gate, is at most 2. So this means that just to have the output depend on all the inputs, the depth has to be at least log n. And now, the major question here, can we come up with an explicit function? We can talk about a function in NP, or even be more greedy and ask for a function in P, for which the depth complexity is omega of log n. That is, we know that every interesting function has depth complexity at least log n, and the question is, can we come up with an explicit function that whose depth complexity is larger than any constant times log n? And this is a major open question in complexity theory that has been open for several decades by now. And it is also known as the not contained in NC1 question. The state of the art here is that we know how to come up with an explicit function in P whose depth complexity is at least 3 minus smaller of 1 times log n. This is a result due to Hastad from 93, and in 2014, Tal improved the lower order terms in this smaller of 1 here. But it has been open for over 30 years to improve the first order term of 3 here. That is to get any constant better than 3 times log n. Questions so far?
And so when we're talking about these very concrete numbers, we're also very specific that we want and or not as our connectives.
We only consider circuits that have and or gates. If we allow the say gates to compute XOR, the constants would be different. If we allow XOR gates, then the leading constant is 2 in the state of the art. Okay, so how do we approach this famous open problem? So one approach to this question was proposed by Karchmer and Wigderson in 1991, and they suggested that we should really understand how the composition of functions behaves. So how do we define the composition of functions? Well, let's say we have two Boolean functions, f that takes m bits and outputs 1 bit, and g that takes n bits and outputs 1 bit. And we want to compose them. Now, obviously, we cannot compose them in the natural way, in the standard way, because the output of g is shorter than the input of f, but we can compose them in the following natural way. So we define the output of the composition to be an m by n matrix. Let's call it X. And now, in order to compute the composition on this matrix, we first observe that the rows of this matrix are strings of length n, so they are valid inputs of g. So we can compute g on each of these rows. And now we get a string, let's call it A, of length M. And now we can compute f on the string A, and we get the output of the composed function x. I mean, we define the output of f on the column vector A to be the output of f, to be the output of the composed function. Now, this is the most important definition in this talk, so if you have any questions, please ask me now. Okay, now given this definition, it is very natural to ask how does how does that complexity behave with respect to composition? And one easy observation is that the depth complexity of the composed function is at most the sum of the corresponding depth complexity. Because if we compute the composed function just according to the definition I just gave you, we will get a circuit whose depth is the sum of the individual depth complexities. Karchmer and Wigderson conjectured that this is not only the upper bound, but that this is actually roughly the right answer. That is, for every non-constant Boolean functions f and g, the depth complexity of f and g should be roughly the sum of the individual depth complexities. And this is a very interesting and natural conjecture on its own right. But the thing is that they observe that this conjecture also implies that phi is different than C1. They observe that if we could prove this conjecture, it would imply that there is a function of super-logarithmic depth complexity in P. It would solve this holy grail question of complexity theory that I mentioned earlier. Now, sometimes people ask me, what do I mean by the depth complexity of the composed function is roughly the sum of the individual depth complexities? Well, there are many different ways to interpret this approximate equality that would yield this implication, and I don't want to commit to one of them, so I leave the approximate equality vague for now. I'll make it into something concrete soon. Okay, so this is a nice conjecture, and it would solve this important question of complexity theory. So what do we know about it? Well, obviously, we don't know how to prove the conjecture yet, or otherwise I wouldn't call it conjecture, but we do know how to prove several interesting special cases of the conjecture. Still, we don't. The results we have don't come anywhere close into proving the full conjecture. And the question is, how can we make further progress now? Well, one observation is that if we don't care about proving the full conjecture, if we just want to get this implication of P not contained in LC1, we don't really need to prove the full conjecture. It's sufficient to prove a weaker conjecture. Typically, if you recall, the full conjecture says that for every Boolean function f and for every Boolean function g, this approximate equality holds. But if we only care about proving about solving the P versus NC1 question, it's sufficient to prove that for every function f, there exists some hard function g for which this approximate equality holds. That is, we replace the for all quantifier here with an existential quantifier, assuming that the function g here is an hard function. And to be a bit more formal, it is sufficient to prove the following conjecture. For every Boolean function f, and for every input length n, there exists a function g from n bits to 1 bit, such that the depth complexity of the composed function is at least the depth complexity of f plus a small omega of log n. Now, you might ask me, okay, this seems ridiculous. You just told us that it is a famous open problem to come up with a function g that has super-logarithmic depth complexity. So why are you allowing yourself? So now, how does it help us that you only ask us to prove that there exists such a function g? Well, the thing is that in this conjecture, the function g is not required to be explicit. We don't care whether this function g, whether the function g in this conjecture is in P or in NP or whatever. In principle, we could prove the existence of such a function g using this easy counting argument I mentioned earlier, and still, if we prove this conjecture in this way, we would get an explicit function in P that does not have circuits of logarithmic depth. Now, in this direction, we do have some partial results. In particular, in 2021, Mihailin and Small proved such a result for the composition of something called the universal relation and the function g. Now, we don't have time to go into what this universal relation is, so you don't need to understand what it is to understand the rest of the talk. Let me just say that if we really want to get any circuit lower bounds, if we really want to get to solve the P versus NC1 question, and we have to take the result and replace the universal relation with a honest-to-God Boolean function f. So this would be our goal from now on. Questions so far? Okay. So this is the main conjecture we will be interested in from now on, the weak KRW conjecture. And now let me tell you a bit about the kind of techniques we used in order to tackle it. So our main tool is called Karchmer-Wigderson relations. This is a classic observation from '89 that says that we can always relate the depth complexity of a function f to the communication complexity of some communication problem that is associated with f, and which we call the Karchmer-Wigderson relation of f. Specifically, Karchmer-Wigderson relation of f, or the KW relation of f, is the communication problem defined as follows. We have two parties, Alice and Bob. Alice gets a string x on which f outputs 1. Bob gets a string y on which f outputs 0. Now, obviously, x and y must be different from each other. So there must exist some coordinate I such that x is different from y on the coordinate I. And the goal of Alice and Bob is to find such a coordinate I. Unfortunately, Alice and Bob don't really like each other, so they don't want to talk that much. And the question is, what is the minimum number of bits that they have to exchange, the minimum number of bits that they have to send to each other in order to find such an index I? And the observation by Karchmer and Wigderson was that the depth complexity of f is equal to the communication complexity of the Karchmer-Wigderson relation of f. In other words, it is equal to the minimum number of bits that Alice and Bob have to send to each other in order to solve the KW relation of f. Using this theorem, we can rephrase the KRW conjecture as saying that the communication complexity of the composed function is approximately equal to the communication complexity of the KW relation of f plus the KW relation of g. Now, it is very useful to view the KRW conjecture from this perspective. So let's talk about how we do this. So for start, let's try to understand how the KW relation of the composed function looks like. Let's recall that the composed function takes input which are m by n matrices. So our goal, so in the KW relation of the composed function, Alice and Bob would take input which are m by n matrices, and their goal would be to find some entry ij such that xij is different than yij. Now, how can they do that? What promise do they have in order to do that? Well, they are promised that the proposed function outputs 1 on the matrix of Alice, and it outputs 0 on the matrix of Bob. What does that mean? Well, it means that if we compute G on the rows of X and Y, we get some column vectors that we denote by A and B, such that if we compute F on A and B, then we get 1 and 0 respectively. Now, it's instructive to see how we can prove that the obvious upper bound using this view. If you recall, we know that the depth complexity of F composed with G is at most the sum of the individual depth complexities of F and G. So the same must hold from the communication complexity perspective. And it's instructive to see how we prove it from this perspective. So let's see it. I'm now going to show you that there is a protocol that solves this problem with complexity is the sum of the individual communication complexities of KWF and KWG. So the protocol is going to go like that. Alice and Bob are first going to compute A and B, and then they are going to notice that A and B on their own are valid inputs to the KW relation of F, because these are a pair of strings. This is a pair of strings on which F outputs 1 and 0 respectively. So they are going to apply the optimal protocol for the KW relation of F and find some coordinate on which A and B differ. Now, after they found such a coordinate, they are going to look at the corresponding rows on X and Y and notice that, G outputs 1 on one of these rows and outputs 0 on the other row. So by definition, these two rows form a valid input of the KW relation of G. So now Alice and Bob can invoke the optimal protocol for the KW relation of G on these two rows and find a coordinate on which these two rows differ. And this coordinate is actually the entry ij that we are looking for. So this protocol invokes the optimal protocols for the KW relation of F and G. So its complexity is indeed the sum of the individual communication complexities. And the KRW conjecture can be seen as saying that this obvious protocol is essentially optimal. Questions so far?
So do we know of, so the intuition is that this is the best Alice and Bob can do?
Yes, exactly.
But do we have any examples of where you can squeeze a little bit out of this and do, or is it like?
Yes, there are also examples in which they can save a bit. I mean, if I remember correctly, there is an example of a function f whose complexity is like 2 log n, but if you compose it with itself, and instead of getting 4 log n, then you get 4 log n minus log n or something like that. And I should say this is not in the standard setting; it is in the setting of monotone theory. But still.
Okay, I see. Thanks.
But we do not. I'm not aware of any example in which we can gain something more than log n.
A quick question, or is this known to be tight? Is this known to be true for monotone, or is that equivalent to general?
Oh, that's a great question. No, we do not know how to prove this conjecture even in the monotone case. A few years ago, we had a result that proved it in the monotone case for any function f and for a large family of functions g, but it is still open if you ask for every functions f and g. Okay. So much for the background. So now let's discuss our result. But before presenting our result itself, I'm starting with a small motivating discussion. So I said that the KRW conjecture says that the obvious protocol should be optimal, but why should it be optimal? Why should we believe it? Well, let's ask ourselves this question, and here is what is to me the obvious answer. Well, first of all, it seems like the players should look for the solution entry ij in a row where the common vectors a and b are different, where ai is different than bi. Why? Basically because these are the only rows in which the players have some kind of a handle. In particular, in other rows, a solution might not even exist. In principle, it could be the case that x and y are just equal on all the rows where ai is equal to bi. So if the players start looking for a solution in rows where ai is equal to bi, they might waste their communication on rows that are equal. Now, of course, if they want to look for a solution in a row where ai is different than bi, they must just find such a row. And to find such a row, they have to solve the KW relation of f. And on the other hand, once they found such a row, I, looking for a solution ij in this row is equivalent to solving the KW relation of G. Sorry. So it seems like in order to solve this problem, the only thing that they can do is to solve both the KW relations of F and G. And therefore, the communication complexity should be the sum of the individual communication complexities. Now, this intuition is very appealing, at least I think it's very appealing. But if you try to turn it into a formal proof, you encounter two major obstacles. First, I assumed here that the players have to find a solution ij in a row where ai and bi are different. And of course, this assumption seems natural, but it has to be proved. And the previous works on this conjecture that proved special cases of the conjecture took great effort and pain to prove this assumption. Second, even if I give you this assumption for free, even if I give you the assumption that Alice and Bob have to solve both the KW relation of F and the KW relation of G, it still does not imply that they have to communicate a number of bits which is the sum of the individual communication complexities. Because, well, this is what's called the direct sum problem. The fact that Alice and Bob have to solve two different problems doesn't mean that they have to pay the sum of the individual costs of this problem. Maybe they have some clever strategy to solve both problems simultaneously and pay less than the sum of the individual complexities. I don't know. There are examples in complexity in which, if you have to solve two different problems, you can somehow solve them simultaneously in a more efficient way than solving each of them individually. Now, so these are the two major obstacles in turning this intuition into a proof. And in this work, we would like to focus on the second obstacle, on the direct sum problem. So in order to focus on this obstacle, we define a notion called the strong composition of the Karchmer-Wigderson relation of F and the KW relation of G. And this notion is defined exactly like the standard KW relation of the composite function, except that we now require the players to output a solution ij where ai is different than bi. That is the assumption that I just discussed in the previous slide. We are now given this assumption for free. Now I should say, I think this definition is not mine. I mean, this is the first paper in which this notion is defined formally and given a name, but it was discussed informally in a lot of discussions among researchers that I participated in the past, and it should be considered folklore. Now, given this notion, it is now natural to ask, can we prove the KRW conjecture for the strong composition of two KW relations? That is, can we prove that for every two Boolean functions, non-constant Boolean functions f and g, the communication complexity of the strong composition is roughly the sum of the individual communication complexities? Now, what's nice about this conjecture, this intermediate conjecture, is first that it is necessary for proving the original KRW conjecture. That is, the original KRW conjecture implies that it also holds for strong composition. So proving the conjecture for strong composition is a necessary step toward proving it for the original composition. And this conjecture is a very natural conjecture on its own right, and it allows us to focus on proving the direct sum aspect, on dealing with the direct sum aspect of the KRW conjecture. So this is what I think is a great intermediate conjecture, and I encourage you all to work on it. What we do in this work is to prove a weak version of the KRW conjecture. That is, we prove that for every Boolean function f, there exists a hard function g for strong composition. More formally, we prove the following theorem. A bit more formally, it's still informal. For every Boolean function f, and for every input length n, there exists some function g from n bits to 0, 1, such that the communication complexity of the strong composition is at least the communication complexity of the KW relation of f plus n, which is the maximum possible complexity for g, minus 0.96 m minus O of log mn. Now, let me say a few things about this inequality. First, we didn't have this term of 0.96 times m, we would be happy. I mean, this would have been an optimal result. We couldn't ask for a better result. On the other hand, if instead of 0.96 here, we had a 1, and this theorem would be trivial. It would be vacuous, because the minus 1 m here would cancel out the communication complexity of the KW relation of f, and we would have a vacuous lower bound. So the only gain here is the difference between 1 and 0.96. And so now you are probably asking yourself, okay, so what does such a result imply? What does it mean? Well, if we could prove it for a standard composition instead of strong composition, if we could prove such a result for standard composition, it would give us an explicit function in P with that complexity, which is at least 3.04 times log n. And this is something that I think would be very interesting, because it would be the first improvement in depth lower bounds in 30 years. Indeed, it's a modest improvement over the previous bound of 3 log n, but still I think it would be very interesting. Nevertheless, it would not be strong enough to solve the P versus NC1 question due to this 0.96 m term here. Okay, questions so far?
Can you say something about why it's sufficient to have just existence of a hard G? Because I guess when you get these results, what you do, you just do repeated composition, right? So somehow, and then it seems like you wouldn't have control over what G you're getting.
Yes. So first of all, in this case, I'll only have one composition, and the second thing is that what you would really do is you will take both the input lengths of both f and g to be logarithmic in the input length you're really going for, and then you can encode their truth tables as part of the input.
Okay. Yeah. Mm-hmm. Makes sense. Yes, I see. Thank you.
Okay. Okay, great. So let me say a few words about our proof strategy. So what we want to do is that, well, we fix some function f over m bits, and our goal is to prove that there exists some function g for which the communication complexity of the strong composition is large. So the first step we do is to move to another communication problem, which is easier to analyze, which I like to call multiplexer composition. And this is and multiplexer composition is defined exactly like the strong composition, except that now G is not fixed, but rather G is of the input. That is, now Alice and Bob are given as input both the function G and the matrices X and Y, and then they have to solve the strong composition of the KW relation of F and the KW relation of G on X and Y for the function G that they were given as input. Now, and it turns out that if we can prove a lower bound for this problem, then this implies the kind of results that we are after. That is, if we can prove that the communication complexity of this problem is at least what we want, the communication complexity of the KW relation of F plus N minus the loss term I mentioned in the previous slide, then we will get a similar bound for the kind of result we like, that there exists a G with the corresponding communication complexity. Now, this transition is not trivial. It's an idea due to Mihailin and Small, and what they proved is that actually, if you can get this inequality in a slightly more sophisticated model of communication, called the half-duplex communication, then this implies the kind of result that we are after. But I don't want to go into this technicality in this talk, so I'm going to ignore it for the rest of the talk. So for the rest of this talk, we focused on proving a lower bound for this problem. So how do we do that? Now, basically, we want to prove that so if you recall, we want to prove that the following protocol is optimal. First, solve the KW relation of F on A and B, then solve the KW relation of G on the I4 of X and Y. Now, and the challenge is to prove that they cannot solve both KW relations together simultaneously faster than solving each of them separately. Now, why do we believe that this is true? Well, my intuition, at least, is that Alice and Bob cannot solve both of them together. Actually, they have to finish solving the KW relation of F before they even start solving the KW relation of G, because until they solve the KW relation of F, they don't know on which row X and Y they should be solving KW relation of G. That is, they only know the index I after they finish solving the KW relation of F. This is an intuition that goes back already to an early work of Edmond Pagliazzo, Rodich, and Gal. And this intuition can be turned into a proof. And the very rough outline of such a proof is the following. We fix a protocol pi for the strong composition, for the multiplexer composition, and we roughly prove that as long as the protocol does not finish solving the KW relation of F, it cannot make progress on solving the KW relation of G. Now this is very informal. I'm now going to make this informal idea into something a bit more formal. So basically, what we are going to prove is the following structure theorem. So let's say we have a protocol for the problem, and we look at a partial transcript of the protocol. If you don't know what a partial transcript is, well, this is just an intermediate state of the protocol. One possible intermediate state of the protocol. So let's look at such a partial transcript or an intermediate state of the protocol. And let's say that this partial transcript, the protocol is still far from solving the KW relation of F, and it only reveals little information about the inputs of the players. Then, after we reach such an intermediate state, or when we reach such a partial transcript, we prove that the players must still must communicate roughly n more bits. Now, this structure theorem is the main technical result of this work. Given this structure theorem, the lower bound we are after follows rather easily, because it is not very difficult to prove that there exists some partial transcript pi1 of length, whose length is the communication complexity of the KW relation of f minus the loss term we are after. That is, we can find some intermediate state in which the players have already transmitted these many bits and satisfies the conditions of the structure theorem. And now we know that from this partial transcript onward, they still have to transmit n more bits. So in particular, we get that in this situation, the protocol must transmit at least this many bits, which is the lower bound that we want to prove. So in the remainder of the talk, I'll talk about how we prove the structure theorem. Questions so far?
I guess you'll tell us later what it means to be far from solving and so on.
Okay, actually, I can do it in the second part of the talk, but basically it measures the formula complexity of f over a partial set of inputs of f that is consistent with the transcript. Okay. So, as I said, I won't have time to really go into the proof of the structure theorem in detail, but I do want to try to mention two nice ideas from the proof. The first is lower bounds using graph coloring. So let's talk about the proof of the structure theorem. We fix such a partial transcript pi1 that satisfies the promise of the structure theorem, and we want to prove that players must communicate approximately n more bits. And in order to describe the technique we are using now, I'll need to define some notation. So now, for every possible function g, I want to look at the set of inputs that are consistent with the partial transcript pi1 and with g. That is, I'm going to denote by the calligraphic x of g the set of matrices x, such that the pair g, x is a legal input for Alice, assuming that we reach the partial transcript pi1. In other words, if we reach the protocol pi1, it is conceivable that Alice got as input g, x. If you recall, we are now talking about multiplexer composition, so Alice gets as an input both the function g and the matrix x. So for every function g, we denote by calligraphic x of g the set of all such legal matrices, and we do the same for y, for matrices y and bob. Now, given this notation, I'm now going to say that two functions g1 and g2 intersect. The corresponding sets, calligraphic x of g1 and calligraphic y of g2 intersect, or vice versa. That is, or calligraphic x of g1 of g2 intersects calligraphic y of g1. Intuitively, if there is such those sets intersect, then I can use it to come up with a counterexample that shows that the protocol failed. What this means is that there is some matrix X that I can give to both Alice and Bob with G1 and G2, or vice versa. Now, a central idea of Mihailin and Small is the following proof technique. They show that if we can construct a large set of functions, such that every two functions in the set intersect, then the players must send many more bits, assuming that we reach this partial transcript pi1. In particular, if the set is V, then they have to transmit a number of bits which is roughly log the size of V. This means that if we want, and it is important to note that this lemma holds even in the setting of standard composition, not just for strong composition. So if we want to use this lemma, this means that we need to construct a set, such a set V of size roughly 2 to the 2 to the n. And if we can construct such a set, we are done. Now, this is a very useful lemma. It's also very nice, but it is a bit difficult to use because this requirement that every two functions in V intersect is quite difficult to satisfy. It would have been nice if we had a more relaxed condition. And one thing we do in this work is to relax this condition a bit. First of all, I'm going to take a graph theoretic perspective into this, and I'm going to define something I call the characteristic graph, and in which the vertices are all possible functions, and there is an edge between two functions if and only if they intersect. And second, and now, given this definition, I can restate the lemma of Mihailin and Small as saying that the players must send at least log the click number of the characteristic graph. So it is the click number omega of g pi 1, where the click number of the characteristic graph is the maximum size of a click in the graph. And in this work, we prove that the players, that this result can be relaxed about the chromatic number instead of the click number. That is, we can show that the players must send a number of bits which is log the chromatic number, which is the minimum number of colors that is required to color the characteristic graph. And this is nice because it turns out to be easier to work with. And in particular, instead of trying to construct a large click, it means that it suffices to prove that every independent set must be small, and this turns out to be a bit easier. Now, as I said, both lemmas work also for standard composition and not just for strong composition. But of course, we want to talk about strong composition, so we want to get something out of it. So let's specialize this lemma to the setting of strong composition. So if you recall, strong composition means that the players have to look for a solution in rows where AI is different than BI. So now in our, so this means that the same result about the characteristic graph holds, about the characteristic graph from the previous slide still holds, but now we need to change the notion of intersecting functions to focus on rows where AI is different than BI. So we change the definition as follows. We say the two functions weakly intersect if and only if there exists a matrix in the set calligraphic X of G1 and a matrix Y in calligraphic Y of G2 that agree on all the rows where AI is different than BI. Now note that in the original notion of intersecting functions, I required that both sets intersect, which can be rephrased as saying that there exists a matrix X in the first set and the matrix Y in the second set that agree on every row. Now, instead of asking that these two matrices agree on every row, I only ask that they agree on every row where AI is different than BI. And of course, the same holds, and also the same condition can hold vice versa if I replace the roles of G1 and G2. And now if I use this definition of weakly intersect, then I can use the same lemma I had in the previous slide for strong composition. So this is the first idea of lower bounds using graph coloring. I hope I can still be able to say a few words about the second main idea, because this is something that might be useful also to people who do not care about the KRW conjecture. So fix 6 sets. So as I said, so we want to use this idea of weak intersection and chromatic number of the characteristic graph. So how can we prove that two functions weakly intersect? Well, basically what we need to prove is that there exists a matrix X in calligraphic X of G1 and a matrix Y in the calligraphic set Y of G2 that are equal on the rows where A is different than BI. And in order to do it, we can use the assumptions that we have on the partial transcript pi1 from the structure theorem. Namely, and these assumptions mean that the sets calligraphic X of G1 and calligraphic Y of G2 are large, because we assume that the players did not give too much information about their inputs. And second, we can assume that the column vectors A and B differ for at most alpha m of the rows for some small constant alpha, because we assumed that at this stage the protocol is still far from solving the KW relation of F. So intuitively, the protocol at this stage cannot force the inputs to differ on it cannot force the column vector to differ on many coordinates. So let's try as a warm-up to first prove that there exists some metrics in calligraphic X of G1 and some metrics Y in calligraphic Y of G2 that are equal at least alpha m rows. And this sounds like a purely combinatorial problem, so let's phrase it in the most general way. Let's say we have some finite alphabet, sigma, and let's say we have two large sets of strings of length m over this alphabet. And now the combinatorial question we are facing is the following. Given that the two sets are large, they are of density at least 2 to the minus epsilon m, that there exist two strings, small x in calligraphic X and small y in calligraphic Y, that agree on at least alpha times m coordinates for some alpha that depends only on epsilon. And it turns out that this is something that can be done. Now, in order to do this, so I describe one solution to this problem that it would be useful for the proof of the full theorem. Now, if I state this toy problem in other words, then it says that there exists some set of coordinates I of size at least alpha m, which the projections of the sets and y to I intersect. And the idea is to choose this set I such that it would be what I call prefix sick, or that these projections would be prefix sick. So I'll finish after more or less slide, or next slide. Okay, so now, what do I mean by a prefix sick set? I mean that if I look at every prefix of the set of strings is prefix sick, if I look at if I look at every prefix of the set of strings, then I can extend this prefix by one additional symbol, and it would still be a prefix in many ways, specifically more than half the size of the alphabet. Intuitively, if someone gives me a prefix of a string in this set and asks me what the next symbol is, then I have less than 1 bit of information about the next symbol or any prefix of the string. And now, one nice property of such sets, which is an easy exercise, is to show that every two prefix sick subsets of sigma to the m must intersect. So this means that if I can choose such a set I of coordinates, such that both projections f, x, and y to the set I are prefix sick sets, I am done. They must intersect. And now, this is another nice idea of this work, and after this, I'm going to conclude. In this work, we prove that if I have some set X that is very large, it has large density, then there are many subsets of coordinates for which such that the projection of X to this set of coordinates is prefix sick. That is, this set of things has many projections that are prefix sick. Now, I should say this lemma is not hard to prove. Actually, it's an easy corollary of a result from the literature of discrete dynamical systems. And the nice thing about it is that it can be viewed as a generalization of the Sauer-Shelach lemma. If you're familiar with the Sauer-Shelach lemma, then a set I for which the projection of x to I is prefix z, sigma is the binary bet, then such a set is, then we call such a set I a shattered set. And the Sauer-Shelach lemma says that indeed for a set x of the Boolean of Boolean strings that is large, we have many shattered sets. So this is an interesting way to generalize the Sauer-Shelach lemma to larger alphabets. Okay, now to wrap up. So the KRW conjecture is a promising approach for proving that P is not contained in LC1, and even a weak version of the conjecture would suffice. And in this work, we consider this notion of strong composition that allows us to focus on the direct sum aspect of the problem. And our result is a version of the weak conjecture for strong composition. And there are a few open problems, but I'll keep them. Thank you very much.
Thank you so much. So while people are thinking about what questions they might have for you, so my first question is, could you please talk a bit about your open problems or where you would go from here?
Okay, so two problems that I think that are on the one hand important, and on the other hand might be tractable. It's first getting rid of this 0.96 m loss in this result. This would have, if we could get rid of it entirely, then we would get a result that, if proved for standard composition, would imply P is different from NC1, which would be very nice. But unfortunately, I have a counter example that shows that getting rid of this loss would require new ideas. That is, the techniques in this work on their own are insufficient to get rid. Actually, you cannot improve it to better than something like 0.63 m using only the ideas in this work. And second, usually when we have such lower bounds for depth complexity, we also get, using the same proof, lower bounds for formula complexity. But in this case, for some reason, it doesn't work. And I would like to know why. And I think that if we can generalize this result for formula complexities, and this would probably yield important techniques and observations.
More questions?
Yeah, thanks very much for the talk. It's very nice. So I had a question about, in general, the KRW conjecture, does it bypass this natural proof barrier, or does it depend on how it's proved or something like that?
Good question. So yes, the KRW conjecture bypasses the natural proof barrier. In particular, it violates the largeness requirement. The thing is that in order to use the KRW conjecture to prove that P is not contained in NC1, what we do is to take, let's say, a random function over log n bits and compose it with itself something like log n over log n times. So we get it. So this gives us the hard function, but this hard function is of very specific form. It doesn't give us a lower bound that holds for a random function. So it passes the largest condition of natural proof.
Okay. But is it just because we construct the function this way? I guess as long as the argument implies a lower bound for a random function, it's still a problem, right?
Yes, but I don't see how it would go, because the argument, I mean, the KRW conjecture only helps if you have like if you have a composition somewhere, but a random function is not expected to be a composition of other functions.
Yeah, thanks.
Sure.
Any other questions, comments? Otherwise, let us thank War again for the seminar. So we are back after the break, and now Or will lead us into a more technical discussion. Please.
Okay, so great. So first of all, let me go over the slide that I missed in the first part that just wraps everything together. So just to remind you what our goal was. So our goal was to prove this structure theorem that says that that we have some partial transcript pi1 that in which pi1 is still far from solving the KW relation of f, and there is little information about the input of the players. And if we have such a partial transcript pi1, then after reaching this transcript, players must still communicate roughly and more bits. Now, to this end, we define this characteristic graph in which every two functions are connected if and only if they weakly intersect. And we show that if we can prove a lower bound on the chromatic number of this graph, then we get a lower bound on the number of bits that the players must communicate after reaching that partial transcript. What does it mean that two functions intersect or that they have an edge? It means that there exists some matrix X in the set calligraphic X of G1 and the set Y in the set calligraphic Y of G2, such that the degree on every row where AI is different than BI, or vice versa. That is, all replacing the same while exchanging the roles of G1 and G2. Okay, and now we said that in order to prove that two functions weakly intersect, we are going to use our assumptions on pi1, which was that the sets calligraphic X of G1 and calligraphic Y and G2 are large, and that that alpha I is different than BI for at most alpha M rows, for some alpha that depends only on epsilon. And then we stated the Warma problem that had to prove that there exists some matrix X in calligraphic X of G1 and matrix Y in calligraphic Y of G2 that are equal on at least alpha M rows. And in order to do so, I argued that I can choose a set of coordinates I such that the projections of both sets to I is what I called prefix seek. And since two such projections must intersect, we get what we want. So and they did it using the following lemma, which said that if I have any subset of strings over some finite alphabet of density delta, then it has at least delta function of projections that are prefix seek. Now, how can I use it to finish the proof of the theorem? So first of all, as I mentioned earlier, using the last lemma, I can find such a set I can find a set I such that both the set calligraphic X of G1 and calligraphic Y of G2, when projected to I, are prefix seek and therefore they intersect. And together with additional ideas, we can prove that many different pairs of functions weakly intersect. This allows us to prove the existence of many edges in the characteristic graph of the partial transcript, which in turn allows us to prove a lower bound on the chromatic number of the graph, which finally leads us to the desired lower bound of the communication complexity. Let me say that perhaps the crucial point is to prove the existence of many edges in the characteristic graphs. once we prove that there are many edges in the characteristic graph, then we can prove the bound on the chromatic number in two ways. Either we can say that there cannot be large independent sets, because if there would have been some independent set that is too large, then we wouldn't have enough edges in the graph. I mean, because we are going to prove that there are many edges in the graph. Or we can use a result from extremal graph theory, Puan's theorem, that shows that every graph that has many edges must have a large clique. Okay, so this is roughly the overall structure of the argument, and from here I'd be happy to discuss whatever part you would like. We can discuss more this idea of proving lower bounds from deriving lower bounds from the graph color, from the chromatic number of the graph, or the lemma about the prefix 6 sets, or we can discuss how we use these two ideas to prove that there are many edges in the characteristic graph. Whatever you like.
Could you maybe go over the definition again of prefix thick sets,
Sure.
just to get a sense of what these sets are and what prefixes are? These are very basic questions, but
yes, of course. So let's say I have a set of strings, or in sigma to the m. That maybe, I mean, let me write you this. Okay, let's say that I have some subset of strings in sigma to the m. Now a prefix of the set is just a string w that can be extended to a string in the set. It is a prefix of some string in the set, calligraphic X. And now a set of prefixes is every prefix can be extended into a longer prefix by one symbol in many different ways. That is, if I have a prefix and I want to add one symbol to it, such that it will remain a prefix, and then.
But when I say, am I fixing the coordinates now? So I think of W as being, if the length of W is something, am I looking at the first, I don't know, K coordinates of X,
yes,
if the prefix has length K?
Yes, I assume some order on the coordinates, and W is prefix, that is, it's the K first coordinate, but I'm not fixing the length of the prefix. I mean, this should hold for a prefix of any length.
Ah, okay.
That is of any length that is strictly less than m, the length of all strings. And it means that if someone gives me some prefix of the set, and I want to, and it asks how many ways are there to add another symbol, to append one symbol to this prefix such that it will remain a prefix, then the number of such prefixes is larger than the size of the alphabet over 2. Put differently, I mean, another way to think about it is that if someone chooses a uniformly distributed string from the set and gives me a prefix of it, I have less than 1 bit of information on the next symbol. But actually, this is a stronger claim, because if one phrases it the way I just phrased it in terms of information, then this is kind of an average case definition. But the definition of prefix 6 that I wrote here on the slide is a worst case definition. It calls for every prefix.
And we are going to use this to argue that, I mean, the second observation that if you have two prefix thick subsets, then they have to intersect.
So let's go over this. So the way I'm going to do it is to construct a prefix to construct a common element of the two sets inductively. I'm first going to argue that there is a common prefix of both sets of length 1. Well, how am I going to do it? I'm going to apply the definition of prefix seek to the prefix of length 0. And well, each of them, so there are more than the alphabet number of ways to extend it to a prefix of length 1 of the graphic X, and there is more than half of the alphabet symbols to extend it to a prefix of length 1 of the graphic Y. So obviously there must be some symbol, some prefix of length 1 that is a prefix of both sets, just by pigeonhole principle or whatever. And then I continue in this manner. So I constructed a common prefix of both sets of length 1. So now I apply again this definition to this prefix both for X and for Y, and I get that there are more than size of sigma over 2 ways to extend it to be a prefix of each of the sets. So there must be one way, at least one way that is common to both sets, length 2. And I continue by induction until I get a common element of both sets.
Yeah. Okay.
So if going backward, so now I had these two sets, X and Y, or let's even look at it from this slide. I have two sets of matrices. The set calligraphic X of G1, which is the set of matrices that I can give to Alice along with G1, and the set of matrices calligraphic Y that I can give to Alice along with G2. And this lemma tells me that there are many ways to choose a set or a subset of coordinates I that or in this case, it's a subset of the rows of the matrices that would make it the prefix seek. Now you should think of every symbol in the alphabet as a whole row. So using this lemma, I can find a prefix seek set, a set of rows such that if I project the matrices in these sets to these rows, I get a set of matrices that are prefix and therefore they intersect. Now, this is not enough. It's not enough to show that there exists some intersection. I mean, it also has to be a set I that is exactly the rows where AI is different than BI, but and this requires some further ideas. But this is the basic approach.
I think I follow this part. I'm a little bit lost in the overall structure of things, so it's a little bit hard to know, like to zoom out and realize exactly what I should ask about. But
okay, so let me go over the structure again. So using this basic approach, I'm going to show that for many pairs of different functions, G1 and G2, I can find such intersection. I mean, obviously, when I describe what I described in the previous slide was very hand wavy. It doesn't work. It cannot work for every two functions, G1, G2, for some reasons. But it requires some more ideas. But basically, I mean, I can explain in more detail how, but the idea is that from this point on, I can prove that many pairs of functions weakly intersect. mean, and this in different words tell me that the characteristic graph has many edges. And now, from now, and actually it's going to be like very, very, a very large number of edges. It's going to be like 99.9999999% edges. Like, well, actually, it's something that approaches to 1 as n goes to infinity. And now, standard result, and now, like a basic argument in graph theory can be used to show that if a graph has many edges, then its chromatic number has to be very large.
But you really need, you're going to use the lower bound on the chromatic number. That was important. Like the clique size is not enough. You're squeezing more juice out of it than that. Is that?
Yes. So actually, when I first wrote the paper, I didn't know how to do it with the clique number. So I wrote this number so I add this lemma on the chromatic number. But later I realized that it's actually possible to use a result from graph theory called the two-ones theorem that says that if a graph has this many edges, it must have a very large clique. So actually, you don't really have to use the chromatic number part. You can use only you can use the original version of the lower bound using a clique number.
Mm-hmm. Okay. Yeah, that was because I was a little bit confused about that. Okay, thank you.
So, I guess just to maybe ask about the parameters here. If I remember right, if your graph has like n vertices, you needed almost like a log n lower bound. You need a clique of size maybe close to n, right? I mean, for the whole thing to work, or how big a clique do you need in this argument?
Okay, so how big I need? Well, okay, so let me change to a word processor. I can answer, but basically, the number of vertices is going to be about 2 to the n, because it's a set of all Boolean functions. Actually, it's going to be a bit less than that because it would be easier to restrict ourselves only to balanced functions, but not going to matter a lot. So the clique number is going, or the clique or the chromatic number is going to be something like 2 to the n minus polylog mn or something like that. Or actually, I think we can even do better than that. I mean, yeah, no, that's the same actually. I mean, this is, I mean, it looks large, but it's really not that large because, I mean,
yeah.
I mean, the thing is that the lower one I'm going to get is polylogarithmic in depth. But if you think about it, another way to write it down is like 2 to the minus. And times 2 to the n, which is, and you can see that this is actually very small. I mean, it's a small fraction of 2 to the n.
So it's almost a polynomial sized clique, not quite. It's almost there, but
okay. A bit larger than that, because I said no, actually, smaller than that. Yes.
Yeah. Okay. Great. Thanks.
And actually, I can find out the exact number. I don't remember it, but okay, that's the precise. I mean, that's actually independence number, but the number is. I mean, the chromatic number is the size, the number of vertices times that. Okay. I mean, I don't know how interpreting that was.
No, it's great. Thanks.
Okay, so
And how do you know how to, I mean, so you're going to find this prefix, like you're going to let Alice and Bob talk for a while.
mhm.
Like how do we, or rather, wait, so
You mean to find this partial transcript I'm working with?
yeah, it's in the, or actually given a protocol tree, I guess you're gonna try to find like a an uninformative transcript, I guess.
Exactly.
Or
Okay, so maybe I can tell you a bit more about what are the precise assumptions I make over the partial transcript. So first of all, let me add a bit more notation. So as before, I have this calligraphic X of G, which is defined exactly as I showed in the slide. And I also want to define calligraphic X of G, comma A, which is the set of matrices that are both consistent with X, that is, I can give it to Alice with G, and consistent with the column vector A, that is G outputs on the matrix. When you apply G to the matrix X, it gives you the column vector A.
mm-hmm.
And I'm going to define the same for Bob. And then I'm going to define the sets of column vectors that are consistent with G. Calligraphic A of G, calligraphic B of G, which are just the sets of column vectors A and B for which corresponding calligraphic X and calligraphic Y are non-empty. These are just the column vectors A and B that have some legal matrices that are consistent with them.
Mm-hmm.
And now what we require for the structure theorem is first that, okay, so there are a few things. First, okay, some font issues here, so let me just write, okay, V0, okay, so let me say that V0 is the set of balanced functions, and what I require is that there is some set of V pi1 of Boolean functions G, for which the following assumptions that I want will hold, that is large, it is 2 to the minus m times all balanced functions. And for each such good functions G, the players are still, the protocol is far from solving a KW relation of F, which means that if I measure the formula complexity of computing F, but only on inputs that come from the set calligraphic A of G and calligraphic B of G, then the formula complexity is very large. I mean, the logarithm of the formula complexity is 1 minus, it's like, okay, 1 minus gamma is just 0.96. It's something like that. So the second item basically says that the protocol is still far from solving the KW relation of F on at this partial transcript, simply because if I think of the residual KW relation or the residual function on the set of inputs that are still consistent with the transcript, the formula complexity of this set of input is still very large. And then I require that for every G in the set of good functions, for every A in the set of good column vectors for this G, and every B for the set of column among the set of good column vectors B for this G, there are many matrices that are the set of matrices that are consistent with G and A or with G of B is roughly large. It's like, oh, actually I wrote it wrong. It's minus 0.04. This is what is really required here. Now, so the as I said, the second item means that the protocol is still far from solving the KW relation of F. The first and second, the third bullet say that the protocol did not reveal much information about the input. In particular, the first bullet says that I did not reveal more than m bits of information about the function g, and the third bullet says that even conditioned on the choice of the metric of the function g and the column vectors a and b, I still did not reveal more than 0.04 m bits information about the metric. Now, the way you construct such a protocol is, I mean, just greedily. You work on the protocol tree and you chose, and each time you choose the next transcript greedily. And you start by, and how do you choose like the next step in the protocol tree? Well, first, you look at every set, at every function g and every pair of column vectors a and b, and you ask which choice of the next step would decrease the size of the set of the corresponding sets of matrices the least. I mean, which step would cause the least amount of harm to the size of the sets of matrices? It is, and you say, oh, and this, so, and then you say, okay, for every function g, a, and b, okay, there is some choice of the next step that would decrease the size of the sets by a factor of at most 2. And then for every g, okay, now for every g, every choice of a and b is associated with some choice of the next step. Now for every g, you choose the next step that if I take this step and throw away and keep only the a and b that it was associated with, it would not reduce by too much the formula complexity of the residual gain. So this means that now for every function g, I have some choice of a good partial transcript. And then you say, okay, there are at most 2 to the m possible choices for the partial transcript. So I choose the one that is good for the largest number of balanced functions g. And this is the partial transcript that I choose. I mean, it's a greedy argument that just have multiple steps.
Could you say something about like where did it come into the picture that G was part of the input? Like how did that work and why is that important? This multiplexer thingy.
Okay, so actually the whole just a moment. So actually this whole concept of characteristic graphs and these lemmas assume that
yes,
it's part of the input. I mean, if G was fixed, then I couldn't.
But okay, but that's a good point. But Alice and Bob are like they know they're getting the same G.
That's right. But okay, that's actually a very delicate point. I'm going to use the fact that yes, I promised them that they get the same G, but there is no way for them to make sure that I actually keep my promise.
Okay.
And what is actually, I mean, the way these lemmas actually work is by actually saying, okay, let's say I break the promise and I give them different G's. What happens now? And the thing is that Oh, okay. Basically, the only way to for them to realize that they broke the promise. I mean, if they can solve the okay. Let me put it differently. The way the proof of these lemmas works is going like this. Let's say that I have a protocol that works perfectly as long as I keep my promise and give them the same function g. So now I can use this protocol as a lie detector, as a way to detect whether I actually kept my promise or not. Let's say I give them now two pairs of inputs in which I don't necessarily give them the same function g. Now I run the protocol. So now I run the protocol, and eventually this protocol outputs an entry that is supposed to satisfy the promises of the KRW game, of the composition game. That is the entry. It's an entry where the entries of x and y are different, and also the column vectors are different. Now the thing is that, okay, if I could find such an entry, okay, sorry. Now the thing is that the functions intersect. I can make sure that they can never find such a legal solution. It's easier to see in the case of standard composition. If the functions intersect, and it means that there is some matrix X I can give to both of them, along with G1 and G2. So if I so now I'm going to run the protocol with two different functions, G1 and G2, and with the same matrix. And now I know that when the protocol ends, it will output some entry that is supposed to be an entry on which the matrices X and Y differ, but the matrices X and Y are known to be identical. So now and this is something that can also be checked very easily, whether the entries of the matrices are equal or not, whether these entries of the matrices are equal or not. So I'm going to run the protocol, and after they output some entry of the matrices, I'm going to check whether the entry that it outputs, whether the matrices are equal on it or not. And what I get from it is this kind of lie detector. If I gave Alice and Bob the same function, I actually kept my promise, and I'll always get, and everything will always work as it should. I'll get an entry of the matrices that is that on which they are different. On the other hand, if I broke my promise, and in particular I gave them two different functions that intersect, then this means there is some matrix X, such that if I give it this matrix to them with G1 and G2, Alice and Bob can detect that I broke my promise. And where am I heading with this? Well, the point is that this gives me a natural non-deterministic protocol for detecting whether functions that intersect are equal or not. So this means that if I have a good protocol for the multiplexer composition, I actually get a non-deterministic protocol that checks whether two functions that distinguishes two situations, whether Alice and Bob get the same function, or whether they got two functions that are neighbors on two different functions that are neighbors on the graph. Just think about the following communication problem. Alice and Bob each get a function, and they want to distinguish these two cases. Either they are equal or they are neighbors in the graph. And the thing is that now Merlin can convince and now I have a protocol for convincing a non-deterministic protocol for convincing Alice and Bob that they actually got two different functions that are neighbors on the graph. I will just run Merlin will choose some matrix X in the intersection of G1 and G2, and now they will run the protocol on G1 and G2 with this matrix X, and they will see that the protocol failed on this input, and therefore they will become convinced that the functions intersect.
Mm-hmm.
So now the question is, okay, so what is the non-deterministic complexity of this inequality problem? This problem in which you have a graph, and each of the players get a vertex, and they are promised that, and they want to distinguish whether they are neighbors or the same vertex. And well, it turns out that there is an old proof of Ronald de Wolf that shows that the complexity of this result is log the chromatic number of the graph.
Okay. Yeah, I think this was helpful. I still need to think about it, but it makes sense.
Yeah, but yes, it's really crucial that they don't know the. I mean, G is part of the input because this way I can somehow play with their minds and give them functions that they are not expecting, that they do not expect to get. Yes, I'd be happy to take more questions.
So do we have any more questions or comments or anything else that would be helpful to clarify? I mean, while you maybe to wrap things up, and maybe while the others are thinking whether there's some final technical questions. I mean, you're on a more philosophical level. So what do we have now? You said like the monotone version of the KRW conjecture is the sort of holds true for, in some sense, a somewhat large range of functions. Here you have this. Here you have this strong composition where you basically force the players to solve both problems the way they should. Well, like, where do we stand? Yeah, where next? And we're in
Okay.
I guess 30 more years from now, will we have solved this? Like, should we be optimistic that progress is happening, or are we stuck, or is it like we're doing this because there's so many other beautiful results that we discover along the way that are interesting in their own right, or how should we think about this?
Oh, okay. So I don't really know, to tell you the truth. I mean, on the one hand, I do see that every few years we manage to bypass another obstacle and prove some result about the KRW conjecture that we didn't know how to tackle before. So yeah, so maybe we should be optimistic. Maybe in a bunch of years we can manage to prove it. On the other hand, sometimes when I work on it, I feel like every such result is just, I mean, peeling another layer of the easy parts of the conjecture, but there is still a hard core of the question that we are not going to be able to tackle anytime soon. I mean, sometimes what I feel like we are doing in these results is just somehow isolating the hard core of the question, but not really making progress on this hard core. And in these times, I am more pessimistic. So I guess my answer is that what I really want to do is to know is to really find out in which case we are. I mean, to keep this feeling until we find out whether there is really a hard core that we cannot tackle with current techniques, or we can go on with the peeling until we finish solving the question. But so yeah, so my personal agenda is let's try to prove more and more results, and hopefully not just any results, but try to do it to prove it to do it in a way that in each time we prove a result, we actually bypass a significant technical obstacle that the previous works could not pass. And actually, this is something that happens in this work. And if someone is interested in, I can tell you more in a separate discussion. And see what's left after we remove more and more technical obstacles. I don't know if this is the kind of answer, that really answers your question.
I think it's fair enough. Yeah. So any final questions or comments before we thank Or again? Oh, I don't see too much by way of reaction from the audience. So then let me thank you again, Or, for this seminar and for the technical discussion. Thank you so much.
Yep.